now we come to the most important part of the afternoon. And in order to review in the proper festive atmosphere, we have some music now, and I hope the musicians are already waiting outside, and I would like to ask them to come in if they are there, which I hope, yes. So, please come in. Let me introduce the musicians to you. We have Erwin on the violin, and Erwin also on the violin, and on the violoncello. And they will play the Allegro from the water music by Handel for us. Please.
Thank you very much. That was really beautiful.
So now the big moment has come. So we need to turn off the light again so that we can see what's on this, what's on the screen. So the big moment is now here. We are going to award the EASY Medal 2022 to Martin Heira. I would like to read the citation that the Scientific Advisory Board of the EASY has written. So Professor Martin Heira from Imperial College London receives the EASY Medal 2022. He is honored for his groundbreaking work on stochastic partial differential equations, SPDEs. Physicists and mathematicians use SPDEs to describe physical systems which evolve in an environment permeated by randomness. However, for the modeling of some fundamental physical phenomena, such as random interface growth, the mathematical tools developed over the past several centuries are insufficient to make sense of these singular nonlinear noise-driven equations, much less to solve them. In a remarkable breakthrough, Heira's theory of regularity structures overcomes this barrier. It provides a powerful and coherent toolbox which has already enabled the solution of several important SPDEs by him and his co-authors and which opens a pathway to new discoveries. And for this, we will give Martin Heyer the ASI Medal 2022. Please, an applause. You can all see how the ASI Medal looks like. Here on the screen, the ASI Medal is made of silver by a company in Tyrol. Actually, there is some relation to your family, right? And Tyrol has a long tradition in silver mining. Perhaps one can say that the silver mining in Tyrol was the first victim of globalization. When silver from the New World started coming in, that was basically the end. That's when it started to go downhill for silver mining in Tyrol. But they're still able to make medals, and that's very good. So the ASI medal has a diameter of 86 millimeters, and it's a 3 millimeter thick. And now it's here in this little box here. This is when you would need 3 hands. So I can show you the medal here. The medal also comes with a certificate and with some money. And I would like to thank the Verein Erwin Schrödinger, the Association Erwin Schrödinger Institute, for helping with this. So let me now, perhaps Miriam, as the chair of the SAB, you can also come to the podium when we give Martin the medal. So this is the medal, and now I will just give it to you. And congratulations. Here is also a certificate. In your office, if you like. So maybe we should take a picture. You in the middle, of course. Thank you very much. So, well, congratulations again.
Yeah, I have one sentence maybe to make. Really, on behalf of the selection committee, I would like to express how delighted and honored we are that you are this year's Schrödinger Medal recipient. Congratulations again.
So you will give your lecture, but before that, I will ask the musicians to play another piece. much. Very beautiful and indeed very awesome. Thank you. All right, so now it's time, I think, to ask Madam Hannah to give the award.
Okay. Well, so thank you very much. I mean, it's really a pleasure to be here. I'd obviously like to thank the scientific board of the ESI, but also Felix, Hendrik, and Jan for giving beautiful lectures today. It was really a very nice afternoon. So the topic I want to talk about, I think was already mentioned in Hendrik's lecture a little bit, which is the stochastic quantization of Young-Mills. And so let me first start by just giving you an introduction of what's the general kind of objects you're trying to construct here. So you have some, so this is, if you want, Euclidean quantum field theory. So it's sort of quantum field theory rotated by 90 degrees in a way. So you're given some actional on a space of fields, and in the case of, remember in Hendrik's lecture, that actional would have been the integral of gradient phi square plus phi 4 dx, right? So that's an example of such a factor, such a functional. The easiest example would just be something quadratic like this, right? And then the goal is to build a measure on a space of fields, but then typically it's going to live on very singular fields, so it would live on distributions, which somehow corresponds to, you know, e to the minus that action functional times Lebesgue measure, right? And of course, you can't define this literally like this because Lebesgue measure doesn't exist on infinite dimensional spaces, right? Now, if the functional is quadratic, right, then you're in good shape because even though Lebesgue measure doesn't exist in infinite dimensional spaces, Gaussian measures do exist in infinite dimensional spaces. And so you can kind of, you know, formally guess the covariance of the Gaussian field from the formal expression for the quadratic expression up here. But of course, that only works in the quadratic case. And then sometimes what you can try to do is you can break it into, like here, it naturally breaks into a quadratic part in the remainder. And so you could try to build it as a, you know, Radon-Nikodym derivative with respect to a Gaussian one. And well, in this particular example, that works in 2 dimensions, but it does not work in 3 dimensions. So in 3 dimensions, for example, the measure that you build in this way ends up being singular with respect to the measure that you would get without that term. Whereas in 2 dimensions, they are equivalent and you do have a Radon-Nikodym derivative. Okay, so that's somehow the general setting of what you want to achieve here. And so the hope is, in general, is you come up with some sort of approximation, like lattice approximation or something like this, and then you try to prove that, you know, there's a limit. And ideally, you would want to have some sort of robustness results that tell you that the limit doesn't really depend too much on the kind of approximation you're taking, right? So it should be sort of natural in some sense. And, you know, of course, so the motivation for the specific model I'm going to talk about today really comes from quantum field theory. But of course, these type of measures also show up very naturally in statistical mechanics. And as you've seen in Hendrik's talk, there was clearly a statistical mechanics motivation where you sort of obtain these as limits of Ising models or stuff like that. But I'm going to talk about the case of Young-Mills, where this action functional here is the Young-Mills action functional. And so the setting here, okay, so I don't want to spend, so Young-Mills theory, so maybe you've heard the word, so I don't assume that people are very familiar with this. It's sort of the theory, or at least it's a big building block of, you know, the standard model. So it's what's actually used to describe sort of nature at a fundamental level. So the important ingredient here is some compact Lie group, and that's some sort of group of local symmetries of your theory. Okay? And so you should think of this as being something like, you know, SON or something like that, so SUN, or that type of Lie group. And here n is not big, right? So it could be like just 3-dimensional or something, right? So it's already interesting if this is a very simple small group. But we're going to think about non-abelian case. Okay, so the abelian case is, from the point of view that I'm going to look at today, the abelian case is trivial. So it should be non-abelian. And then what plays the analog of fields is really sort of equivariant connections on the torus, or I mean, the torus here is your configuration space, times the Lie group, or in general, it's a principal bundle. And one way of looking at this is as one forms that take values in the Lie algebra. So that's your space of fields. Okay, so the analog of the phi's here, this time are not scalar functions, but they're essentially something like one forms, but not real valued one forms, but they are one forms that take values in the Lie algebra of that Lie group G, okay, which is still just a finite dimensional vector space. And then the action is some kind of curvature of this. So whenever you have a connection, right? So why is this a connection actually? What does a one form have to do with a connection? Basically, you know, the picture you should have in mind is that, you know, you have your, say, 2-dimensional torus. At every point, you attach a copy of your group G, right? And now, what you should really have in mind is that, you know, there's a symmetry of your space which says that you should really think of this as being a copy of the group G where you've forgotten where you put the origin, right? And so you don't have natural way of identifying, right? The way I drew it here, of course, you know, there's in some sense every copy of G has an origin, and so there's a natural way of identifying them. Now, if you forget about where the origin is, okay, then that means that if you're given a path downstairs here, so the yellow one is a path that takes values in just the torus. And now, given such a path, you can ask yourself, you know, is there a natural way of lifting it to a path that takes values in torus times G? And now, of course, if you know where the origin is, well, then there's a stupid way of lifting it, right? Is we're just at every point, you just go through the origin and then that's it somehow. So that's not interesting at all. But now, if you've forgotten where the origin is, then suddenly there isn't a canonical way of lifting it anymore. And so you can provide a way of lifting it, and that's a connection, okay? But now a connection is just basically a local way of lifting it. So it just says, well, you know, if at some point, say here, you go through this point here, and now downstairs, so say downstairs is that point. So say downstairs, your curve points in a certain direction. And now I have my other copies of G that go along here. And then you can, you know, you have to specify in which direction you're going to move upstairs, right? And you want to do this in a sort of natural way, in the sense that, you know, if instead of going through this point, you go through this point here, then of course, the direction in which you're going to go here is going to be the same as just going in this direction and then moving it by, you know, just multiplying, if you want, by the element of G that gets you, right? So there's one element of G that gets you from this point to this point, and that multiplication map, you can just take the tangent map of that multiplication map that sort of moves that vector to somewhere. And, you know, you would want to have, this kind of compatibility, if you want, right? So now you can kind of see why G-valued one forms are the relevant object here, because if I give myself, if you want, a coordinate system, so coordinate system is, in this sense, is choosing an origin for each of these copies of G, right? So if I've specified an origin for each copy of G, so that means that in principle, I do have some way of identifying all these copies, but it's sort of arbitrary because I've just chosen an origin. It wasn't canonical. But then with respect to that choice of origin, now it gives me the coordinates that I need in order to describe, these blue, right? So the procedure that turns a tangent vector here into a tangent vector on the overall space, which of course should project down to that one. And so the missing piece is by how much you're moving sort of in the G direction. And that's an element of the tangent space of G, which is the Lie algebra, right? And so therefore a connection here really should just be a one form that takes values in the Lie algebra, right? So that's sort of the natural object in this business. So that's your fields, okay, in Young-Mills theory or engage theory. And then the action, whenever you have such a connection, there's a notion of curvature, and essentially the curvature is sort of an infinitesimal. It tells you by how much, this procedure of lifting curves isn't quite consistent, isn't integrable, right? So it gives you sort of a measure of non-integrability in the sense that even if I take a closed loop down there, right, and if I lift it, there's no reason a priori that it closes up, right? If at every point I just provide you with a recipe of how to lift it sort of locally, then you lift, you go around, and you may end up in the same fiber, but you may not end up at the same point in that fiber, right? And the curvature of a connection is basically a local measure of this non-integrability by how much you sort of end up not being in the fiber. And so that's basically that's a two-form, right? So it sort of tells you if I take like a little plane downstairs and I take a little loop in that plane, how much is it not going to close up, right, if I lift it? And so that's what this curvature guy measures. That's what, even the natural Riemannian curvature that you're maybe more familiar with has an interpretation like that as well, right? And so the action functional here is just the L2 norm, if you want, of that curvature. Now, the interesting feature of these kind of gauge theories is that they have a very large symmetry group. And here the symmetry group is basically the changes of coordinates that keep the base space invariant. So it's essentially, changing the choice of origin or changing the choice of unit for each of these copies of G, right? So your symmetry group consists basically of smooth functions from the torus into G. And the way you should think of it is essentially just changing the choice of, which point is the origin for each of these copies of G, right? And it's obviously a group by just pointwise multiplication in G. So that guy acts, so there's a natural way in which it acts on these connections, which you can kind of, if you sort of, even if you haven't really seen this before, from that picture in principle, by sitting down for 20 minutes or something, you could probably figure out what the action should be. And if you do the calculation, you found that, it acts on these connections in this way. So that, in some sense, that shows you that these connections, even though they are described by one forms, intrinsically, they are not actually one forms, right? Because they are described by a one form only modulo one specific choice of one section of your bundle. If it was a one form, then the gauge group would just act by conjugation, and here it actually acts by conjugation plus this extra term. And if one, plugs this into the definition of this curvature tensor and just looks at what happens, then that guy, one can see that this one is an actual tensor. So that one, the gauge group just acts by conjugation. And then the norm here is the norm which is a invariant under conjugation, and therefore that guy actually doesn't change, right? And so this whole action here is invariant under the action of this gauge group, okay? In the sense that S of AG is equal to S of A for every A and for every G. Okay, so in that sense, it's invariant. Now, why is that? Okay, so why is this interesting, or why is this a problem in this program, if you want? Well, the problem is that now if S is invariant under the action of an infinite dimensional group, right? That means that, well, S is basically by definition, it means that S is constant on each orbit of that group. Now, if the group is infinite dimensional, well, chances are that the orbits are also going to be infinite dimensional, right? Because the action here is maybe not completely non-degenerate, but it is sort of non-degenerate enough so that the orbits are still infinite dimensional. And so that means that your S is basically flat at every point. It's sort of flat in infinitely many directions, right? And then that's a problem if you want to look at the measure e to the minus s times Lebesgue, because it means that there's still infinitely many directions in which it kind of looks like Lebesgue measure, right? And we know that Lebesgue measure doesn't exist in infinite dimensional spaces, right? And so that means that sort of on the face of it, unlike here, right? So here, it really grows. These are very coercive kind of functionals, right? So this really grows in all directions. In phi space, it sort of grows very fast in some sense in all directions. This action functional is not coercive, right? Because it has sort of infinite dimensional degeneracy. So, okay, so that tells you already that in some sense it's hopeless to try to define some measure even on spaces of distributional connections, which somehow corresponds to, at least naively, to this e to the minus action. Now, yes?
The statement, we do that via Fourier-Popov procedure.
Right, so there's different ways of fixing this. And so the good news here is that what you're interested in is only in physically relevant observables, if you want, and those are observables that are constant on the action of the gauge group, right? So on these orbits, physically relevant observables don't see, if you want, where you are on the orbit. And so what you would really want to do is not construct a measure on space of connections, but on the quotient of the space of connections by the action of the gauge group, okay? Or if you want, you could, another thing one could try to do, which is to say, well, you know, I have my space, say I have some connection here. If the board here is the space of all possible connections, the yellow line would be an orbit of the action of the gauge group on this space. So that's an infinite dimensional space. The yellow line is also an infinite dimensional sort of submanifold, if you want. Now, you could say, well, instead of building a measure on equivalence classes, I could just choose an element of each equivalence class, for example, right? So that's what's called gauge fixing. And then you would want to build measures on, if you want, that red space, where now there's chances that things are much more coercive. Problem is that this globally here, the gauge fixing thing doesn't work very well. And if you try to do it with this stochastic procedure, it gives you things that look very ugly. So we're going to do something a bit different. So just in terms of what are the natural kind of observables that show up here, well, the natural observables are exactly the ones that are already hinted at. which are you take a closed loop, and then you look at the holonomy that corresponds to that loop, which is basically you lift your loop, you go around the loop, you look at how much you move, and then you look at the, the conjugacy class of the amount by which you're going to move. And that's a quantity which one can show is invariant under these gauge transformations. And basically every other gauge invariant quantity can be approximated by functions of these Wilson loop observables. Okay. And still, okay, so as already mentioned, you would really want to, in some sense, quotient out connections by the action of the gauge group and build a measure on that quotient space. But then it's still, well, it's not so clear a priori how that quotienting then manifests itself at the level of the measure. Right? Quotienting operation is not a terribly nice operation if you describe a measure in terms of density against something like Lebesgue. Right? And it's not clear also if you want to build an actual measure, right, you need to actually specify some space. Now, my connections are going to be, well, we expect that they would be distributions. So then you end up quotienting some space of distributions by some space of gauge transformations. But then it's not completely clear, right, how the quotienting procedure should actually work, because if you quotient out by smooth gauge transformations, you're not going to get a nice space, for example, because that would be a little bit like, you see, imagine that you take the space of continuous functions, and then you look at the action of smooth functions by addition onto continuous functions, and then you quotient out by that. Then that quotient space would be something absolutely horrible, right? It doesn't have any nice analytic properties at all. So it's a horrible topological space. For example, there are basically no non-constant measurable functions on that space. So it's not a space on which you can do any probability theory, right? So you want somehow the topology on your gauge group to be somehow compatible, right? You would to put a topology on it, which would not be the topology of sort of smooth gauge transformations, which is sort of compatible with whatever topology you put on your connection so that your quotient space becomes something reasonable. Right? Okay, so let me just give a few just literature pointers about what's the sort of constructions that were done before in the mathematical literature. So of course, there's a lot of work in the physical literature on Yang-Mills. So this here I'm focusing only on the mathematical literature. In 2 dimensions, so actually in 2 dimensions, there is magic happening, as it so often does in 2 dimensions, and there's some kind of integrability properties of the theory, which means that one can come up with an explicit construction of the, so if you take k different loops, and then you can ask yourself, what is the joint distribution of k of these Wilson loop observables under this measure? You can do a formal calculation that actually suggests a formula for the k-point distribution. So you have a somewhat explicit formula for the k-loop distribution. And so in 2 dimensions, in some sense, you can build the measure like that. Right? So that still doesn't really give you a measure on a nice state space. So it's a little bit like the difference between specifying a stochastic process by k-point distribution, as you would do in Kolmogorov extension theorem, or specifying it by an actual, probability measure on a space of continuous functions, which then something like Kolmogorov's continuity test would allow you to do, right? So that would give you something like, the k-point distribution. There are actually recent theorems, so there's in particular a recent theorem by Ilya, which provides an analog in this context of something like the Kolmogorov continuity test. And so you can really build a space of distributional connections so that this measure or like these k-point distributions can be realized as really, the k-point distribution of the Wilson loop observables of a probability measure on some space of distributional connections. That can be done in 2 dimensions. And so there's, of course, a lot of work. For example, there's recently quite a lot of work by Thierry Lévy, which exploits these explicit formula for the k-loop distributions in 2 dimensions. In 3 dimensions, one doesn't have any kind of explicit formulas. So there's a series of works by Alaban and then a number of other authors that sort of go back to I think the earlier works are in the 80s, but then there are sort of later works throughout the 90s and the 2000s. And the approach there is somewhat similar to the Klim-Jaffe type approach on 5-4 in 2 and 3 dimensions. So they obtain some type of stability on the removal of the ultraviolet cutoff in these works. But it's not complete. It doesn't actually build a probability measure on a state space, right? So it's not completely clear what one ends up building. There's a candidate state space that was kind of recently proposed by Kao and Chatterjee in 3 or 4 dimensions, or in any dimension really, but it's only relevant in 2, 3, or 4 dimensions. And that's going to be, in some sense, closely related to a state space that we end up having in our results. Okay, so now the approach that we're going to do towards trying to make steps towards the construction of such a measure is, well, this stochastic quantization approach that Hendrik already mentioned in his lecture, which was proposed by Parisi and Wu in the early 80s. And they actually proposed it precisely in the context of Young-Mills or gauge theories as a way of dealing with gauge theories without actually having to do a gauge fixing, or without having to do sort of specifically have to do some kind of gauge fixing procedure. And the basic idea in general, so for any measure of the form e to the minus some action times Lebesgue, so the general idea is that, well, if it were finite dimensional, right, so if you just have on Rn, you have any measure of the form e to the minus something times Lebesgue, then that measure is invariant for some kind of noisy gradient flow, right? So if you just take the gradient descent for the potential that shows up in your measure, right? So that's your potential. So you take the gradient descent and then you add some noise to it. Then you can check that at least formally that measure is invariant for the evolution of that random, so of that stochastic differential equation, in the sense that if you start with an initial condition that's distributed according to that measure, and then you run that differential equation for any fixed time, then the solution after that time still has the same distribution. And if you start with any other distribution, it's going to converge to that distribution as time goes to infinity, under various technical assumptions. And so then the hope is to say, well, okay, so let's just close our eyes, write down, pretend that the thing is finite dimensional, but of course it's really is infinite dimensional, just write down the equation that this would give you, right? And then if you can give a meaning to the equation, then you can just define the measure you're after as being the measure that's invariant for that equation. And then maybe if you're more ambitious, you could go back to the 2-dimensional case where the measure was already constructed and check that at least in that case it's the same. So that would be some kind of reality check. Now, if you do that, in this case, the equation that you get is the following. So I don't really want to introduce the notations too much, but they are essentially, deformations of the usual kind of exterior derivative operator from differential geometry. And so you get some term that looks a little bit like a deformation of the Laplacian here. And then you get some additional term. The problem here is that, I don't know if you remember, but if you take the operator d star d and you apply on forms, this is not actually a Laplacian, right? So the Laplacian is not d star d, it's d star d plus dd star. So if you just take the d star d, it's not actually an elliptic operator. And that's, of course, to do with the fact that you have this infinite dimensional degeneracy somehow, right? So locally, in some sense, there are infinitely many directions in which your gradient descent doesn't improve things, okay? And that's somehow reflected in the fact that this operator here is not parabolic or not elliptic for the right-hand side. So it looks like this, right? So if you write it in coordinates, it's sort of there's a heat equation part, but then there's this additional term, and then there are lower order terms, lower order in the sense of derivatives of lower order, right? Just first order derivatives or no derivatives at all. Now, the idea then is to say, so that's the analog, if you want, of gauge fixing in this context. The idea is to say, well, I could, if I have some kind of evolution in that space, and I only care about looking at it through observables that don't distinguish points on these orbits, and if the evolution furthermore is sort of gauge equivariant in the sense that if I start from a point and look at my evolution starting from that point, and then start from a different point on that orbit, and look at the evolution starting from that different point, right? So you would want a property which formally is satisfied by that equation, which says that I can obtain this solution by basically taking this solution here and then acting on it with some gauge transformation, or maybe a random gauge transformation or something, right? And so that's, at least one can check that formally that's verified. And so then you could say, well, I could simply add at every point some additional drift that pushes me somehow in the direction along these orbits, right? So the effect of that additional drift, so now I'm looking at a completely different process, but if I only look at observables that don't distinguish points on each orbit, right, then they wouldn't really tell the difference. Because if now I get pushed a little bit here, well, I restart from here if you want, instead of starting from here. But I was saying, well, my assumption was that this guy is just obtained as a gauge transformation from that guy, and so I wouldn't see the difference between these two guys, right? And so I can do that instead of doing it as by jumps somehow like this. I can do it sort of in continuous time all the time. I can just add some additional drift term to my equation, which sort of pushes me in the direction of the gauge orbit at every point. And it turns out that, well, if you do the calculation, basically any term of this type, so you take any functional of your connection, any functional h of a, and then you take this covariant derivative of that functional. So anything of that form formally gives you, a vector field, if you want, that goes in the direction of the gauge orbits, that goes along the gauge orbits. And there's one natural choice here now, is to take h of a to be minus d star a, because then you just, right, so then that dd star will just give you the additional term, right? Here you had a d star d already, and so that creates the additional term which gives you a Laplacian. Right? And so that was a trick that was first actually discovered by the Turk in the context of the Ricci flow, where there's a similar kind of problem showing up. And then Donaldson realized that that trick in exactly the form that I just mentioned works for Young Mills. Okay, so now, right, so that was just the same picture here. So now if you do this, your equation you end up with is somewhat of this form, right? So it's now parabolic. and there's a bilinear term in A and its first order derivative, and a trilinear term in A. And so now in principle, it's more or less of the same form as this phi-4 equation that Hendrik wrote down, right? So which only had the trilinear term and didn't have the bilinear term. So it's sort of a mix between something like this phi-4 and something like a Navier-Stokes type nonlinearity. So now this whole theory that you just heard about applies. And so then you can just, so at this point you would think, well, okay, so you just plug this into that machine and that builds your solution theory. Then, okay, fine. So you can do that, right? So you just apply, you mollify that noise, and then you have to pass to the limit. But remember, there's this randomization business. So you can't just pass to the limit in the original equation. In general, it won't converge, right? So the theorem is always you regularize the equation, and then there's a way of adding counter terms that makes it converge. And there's a somewhat explicit recipe that tells you what the counter terms look like. So in this particular case, if you do a bit of work, what you find is that the counter term is like this. It's sort of the same as in phi-4. If you want, it's basically just a linear term with some diverging constant out in front. And so, okay, so the theory tells you, well, there's a way of choosing this constant that makes this converge. But now there's a problem, right? Which is that this equation had this nice symmetry, right? So there was this gauge invariance, which said that if you start from a different point on the same orbit, then if you sort of project the solution, I mean, that's of course not a theorem, it was just a formal calculation, right? It's something that you would hope to be true for the process that you're building. But you would want your process to have the property that if you start with two different points on the same gauge orbit, and then you just sort of project the processes onto the space of orbit, you get the same process. Basically, that when you project down, you'd still retain the Markov property. Right? That's the, if you want, the relevant form of gauge invariance in this context. And formally, the equation, this equation here, formally has that property, right? So you can do, if you just pretend that the equation is well posed, then you just sort of, try to figure out how it behaves under gauge transformations. You can see that if you start with a different initial condition, which is related to the original one by a gauge transformation, then you can write down a PDE for the gauge transformation to make it time dependent, so that if you then take the solution starting from the original initial condition and you transform it with the solution to that PDE, right, as your element of the gauge group to give you a solution, then the new guy solves exactly the same equation, the only difference being that the noise gets conjugated by that gauge transformation, but then that's an orthogonal transformation. And so by E2 isometry, it has the same law as the original noise, right? So that's somehow the argument. But it's completely formal. It essentially just assumes that we have some kind of solution theory and that the rules of calculus and of Ito calculus and so on are sort of the rules that you would expect to be true, right? So now what happens here is you add this extra term. And so now if you do exactly the same calculation, well, it breaks down, right? So it would suggest that the thing is no longer somehow gauge invariant, right? Because this term by itself is not gauge invariant, basically because of the way that gauge transformation acts on A, right? It acts not just by conjugation, but conjugation plus this additional term. And that breaks the gauge invariance of that equation. But on the other hand, the fact that you've regularized the noise breaks it as well, because the calculation I just mentioned to you relies on the fact that conjugating the noise with basically an arbitrary element of the gauge group gives you something that has the same law. but that really relied on E2 isometry in L2. And well, if you mollify the noise, then if you want your E2 isometry is no longer quite in L2, but there is a sort of, well, the covariance, the mollifier that you used here kind of shows up, and your calculation breaks as well, right? So if you do this, basically you've broken gauge invariance in two different ways. On the one hand, by regularizing the noise, on the other hand, by adding this extra term, right? And so then the question is, is there a miracle, right? So sort of like the miracle that you would expect is that the two ways in which gauge invariance here is broken, they magically compensate in such a way that it actually isn't broken in the limit, right? So that's what you would want to prove. And that, of course, the theory doesn't tell you anything about that, right? It just tells you, oh, there's a way of choosing these constants so that these guys converge to a limit. So at least you know that there is a limit, okay? But then you want to know something about properties of the limit, okay? And so the theorem is that, well, I mean, of course, you can kind of see where this is going now, right? So obviously the theorem is that the magic happens, right? And what's interesting here is that, you see, here, if you choose, there's a way of choosing that constant that makes this guy converge to a limit, but if you make the same choice plus 25, then it also converges to a limit, right? To a different limit. And if you make that choice plus 78, it converges to yet another different limit, right? So you have a one parameter family here of possible limits. And nobody tells you what's the right choice of that constant, right? So it just tells you that there's a way of choosing it so that you converge, but it's always just sort of modulo finite part. And you can choose that finite part in any way that you want, and you're just going to converge to different limits. Right? So you're going to have a one parameter family here of Markov processes. And you want some kind of principle that would choose the right one, okay? And so what the theorem tells you is that, okay, so that's the point 4, which is somehow the most interesting one, is that there is exactly one right one, right? So you get a one parameter family of these Markov processes in the limit, but there's exactly one guy in that one parameter family which still has that property, right? Which still has the property that if you start from different points on the same orbit and you project down on the space of gauge orbits, you don't see the difference, right? Whereas if you choose any other element in that one parameter family of solution theories, it would not have that property, okay? So that's in that sense that sort of the magic happens, that you can recover this gauge invariance in the limit, the one that you sort of saw at the formal level. Now, and the other bits, they are sort of more technical kind of statements, but they're basically saying that you can build a nice state space, right? So you can actually choose a good space of distributional connections so that if you take as your space of gauge transformations simply the Hölder continuous ones, right? So that's a very natural space of gauge transformation. So not just the smooth ones, but actually all the Hölder continuous ones for some Hölder exponent alpha, and alpha has to be, and here one has to choose it somewhere between 2/3 and 1. You can take any value between 2/3 and 1. Then there is a corresponding space of distributional connections so that the quotient space is actually a nice space, right? So it's a Polish space in the Harlands. Maybe you can just say a couple of words about distributional connections. So what's the natural notion of distribution for connections, right? So it's not, and of course a connection you could say, oh, I just write it in components, and so my A has components AI, and then a distribution connection is just somehow AI so that each AI is a distribution, right? That's not the natural notion of distribution for a connection. So the natural notion of distribution for a connection is, well, what do you do with one forms, what are here, right? So what do you do with one forms? You integrate them along lines, right? That's kind of what one forms are good for. And so a natural notion of somehow distribution for one forms is just like for regular functions, the way you define distributions, you say that, well, my operation is testing against test functions, right? And so then I just postulate what the value is when I test against an arbitrary test function, and I want to impose some compatibility, which is just linearity in that case. So here, I say, well, what can I do is integrate along line segments. And so this notion of distributional connection is simply a map that maps a line segment. So a line segment being, an arrow like this, which has a starting point and an end point. And so which maps each of these guys to a number or an element of the Lie algebra in that case, because it's a Lie algebra valued one form, with the property that, well, if you take two arrows that point in the same direction and just follow each other, then of course the sum of these two numbers should be the same as the one for the arrow that goes from here to here, right? So that's the natural compatibility condition in this case, which sort of replaces linearity. And then you can impose some kind of regularity now. So on the one hand, you can impose some kind of small scale regularity, which tells you how big that number should be if the arrow is very small. And so if your one form was a normal one form, so if it had an actual continuous density, if you want, then that would be of the order of the length of the arrow, right? So if I take a regular one form and I integrate it against a little arrow, against a little line segment, I'm going to have a bound which is just of the L infinity bound times the length of the line segment. And so now here you can weaken that by imposing a bound which is just line segment to the power alpha, right? Some kind of holder type bound, but for alpha less than 1. So that means that now, in some sense, that corresponds to a distributional kind of one form. And then you want a bit of regularity that goes sort of, that tells you that if you take two arrows that are sort of almost parallel like that, right, then of course the two numbers that you get should be close. Right? So you want some kind of regularity also in sort of lateral directions. And so that gives you these spaces, omega alpha here of distributional one forms. And if you define the topology on these spaces in the right way, then you can make sure that that quotient space is actually a very nice topological space. So then you have a genuine, an actual state space, which is a perfectly nice space on which you can do probability theory, and you've built a Markov process on that space. And then, of course, the conjecture here, so that's in 2 dimensions, right? So in 2 dimensions, you had a candidate for the Young-Mills measure. And so, of course, the conjecture is that that candidate is invariant for that process, but that's not quite a theorem yet, but it's sort of not very far from being a theorem. In 3 dimensions, there's a few bits that go wrong. So for example, in 2 dimensions, the fact that this magic happens, with these 2 ways of breaking gauge invariance that then cancel out, it comes essentially from an explicit calculation. So you can somehow compute the values of these randomization constants, and you see that there's a cancellation. In 3 dimensions, in theory, you could do a similar kind of explicit calculation, but it becomes completely intractable because there's, in 2 dimensions, the constant sort of 3 bits, each of them diverges logarithmically, and you just compute all 3 of them, and you see that there's a cancellation. In 3 dimensions, there are 3 bits of order 1 over epsilon, and exactly the same cancellation happens, and you can check it. And then there are logarithmic terms, and there's like 100 of them or something. And so they're completely intractable. and they are much more complicated. So there would be sort of 5-fold integrals over heat kernels or something. It's completely impossible to do the calculation, right? So here you have to come up with a different argument, and so you can actually do it. So in 3 dimensions, you can come up with an argument that it tells you that this cancellation has to happen without having to actually compute it. Then these Wilson loop observables don't really exist in 3 dimensions because there's essentially it has to do with the fact that the free field in 3 dimensions can't be restricted to lines because the covariance goes like 1 over x, and 1 over x is not integrable in 1 dimension. Then also, in some sense, the state spaces that we use, they only make sense somehow for alpha bigger than 2/3. At some point at 2/3, there's part of the construction that breaks down. And in 3 dimensions, you would want to go sort of just below a half. And so there's about a 1/6 missing, a little bit more than a 1/6 missing. And then even if you had it, there would be the problem, right? So even if you were able to go down to a half, in 2 dimensions, we could produce this nice quotient space, somehow now spaces of distributional connections by the space of gauge transformations. Even if you could take alpha equal a half or just slightly below a half, then you would have exactly that problem, right? So in some sense, taking that, the prerequisite of being able to take the quotient is to actually have an action of your group on your space. And now the action of the gauge group is essentially like a multiplication, right? Because there's conjugation of the gauge transformation with your connection, and then there's this additional term, GDG inverse. When alpha hits a half, both of these terms become ill-defined for exactly the same problem that Young integration kind of breaks down at a half, right? And so you don't actually even have an action of that gauge group, and so then you have to sort of relax your notion of what you mean by a gauge orbit in that case. And so we still have some partial results. So that's recent results. Oh yes, I forgot to say actually. So all of what I've been talking about is joint work with AJ Chandra at Imperial, Ilya Shevirev, who's in Edinburgh, and Hao Shen, who's in Wisconsin-Madison. And so there's a quite recent result in 3 dimensions where we have somehow an analog of the 2-dimensional result, but the results are much weaker. And they are weaker because of these topological problems that we don't have good ways of taking the quotients of these spaces, but we can still define a notion of gauge orbit. There's still a natural way of defining it. And we can define a Markov process, and we still have that, gauge invariant. So we can still define an actual Markov process on the quotient space, modulo possible blow up. And here in that particular case, so in 3 dimensions, the state space that we end up building is actually quite similar to the space that Kao and Chatterjee were proposing at around the same time. Okay, so I think we are I think I've already run over time. So here I just put there's a few open questions that are still, to be investigated in that direction. And well, thank you very much. That's it.